Arnold Sommerfeld's 1915 magnum opus, Atomic Structure and Spectral Lines, represented a pivotal moment in the evolution of quantum theory, extending and refining Niels Bohr's groundbreaking model of the atom. This work, more than merely a synthesis of existing ideas, incorporated relativity and advanced mathematical techniques to provide a more nuanced and accurate description of atomic spectra, laying the groundwork for future developments in quantum mechanics. The intellectual landscape preceding Sommerfeld's work was dominated by the successes and limitations of Bohr's model, proposed in 1915. Bohr had successfully explained the discrete spectral lines of hydrogen by postulating that electrons could only occupy specific energy levels, transitioning between them by absorbing or emitting photons of corresponding energies. Bohr's theory, while revolutionary, possessed shortcomings such as its inability to explain the spectral lines of more complex atoms, the fine structure of spectral lines, and the Zeeman effect, the splitting of spectral lines in a magnetic field. Moreover, Bohr's model relied on a rather ad hoc mixture of classical and quantum ideas, appealing to classical orbits modified by quantum conditions, a theoretical patchwork that felt unsatisfactory to many physicists. Sommerfeld's approach was to retain the fundamental principles of Bohr's model while incorporating elements of classical mechanics and relativity to address its deficiencies. A key innovation was the introduction of elliptical orbits for electrons. In Bohr's original model, electrons move in circular orbits, characterized by a single quantum number, n, representing the energy level. Sommerfeld, however, recognized that, following Kepler's laws of planetary motion, electrons could move in elliptical orbits with varying eccentricities. This necessitated the introduction of a second quantum number, L, the azimuthal quantum number, which quantified the angular momentum of the electron and determined the shape of the elliptical orbit. The azimuthal quantum number could take values from 0 to n-1. This addition permitted multiple orbits with different shapes to possess the same principal quantum number, further allowing for the splitting of energy levels. The introduction of elliptical orbits, while enhancing the model's descriptive power, introduced a further complication. According to classical electrodynamics, an electron orbiting a nucleus should continuously radiate energy, causing it to spiral into the nucleus. Bohr's model circumvented this problem by postulating that electrons in stationary states did not radiate. Sommerfeld retained this postulate but needed to ensure that the introduction of elliptical orbits did not reintroduce the problem of radiation. This meant that classical mechanics alone could adequately describe the motion of electrons. Sommerfeld integrated the Sommerfeld quantization rules. These rules, derived from the work of William Wilson and John Ishihara, quantized the action integral, a quantity related to the energy and momentum of the electron over one complete orbit. The Sommerfeld quantization rules ensured that only certain elliptical orbits were permitted, preventing the electron from spiraling into the nucleus. Mathematically, the quantization conditions were expressed as the integral over the generalized momentum dq sub I with respect to the generalized coordinate q sub I, taken over one period, equals n sub I times Planck's constant, where n sub I is an integer quantum number. Perhaps Sommerfeld's most significant contribution was the incorporation of special relativity into the atomic model. He recognized that electrons moving in elliptical orbits, particularly those with high eccentricities, would experience significant variations in velocity as they orbited the nucleus. These velocity variations would lead to relativistic effects, such as the increase in the electron's mass with velocity. Sommerfeld calculated the relativistic correction to the energy levels of the hydrogen atom. This correction, proportional to alpha squared divided by n squared, where alpha is the fine structure constant, a dimensionless quantity approximately equal to 1/137, and n is the principal quantum number, accounted for the fine structure of spectral lines, the small splitting of spectral lines observed at high resolution. The relativistic correction effectively lifted the degeneracy of energy levels with the same principal quantum number but different azimuthal quantum numbers, resulting in the observed fine structure. Sommerfeld's relativistic model provided a remarkably accurate description of the hydrogen spectrum, accounting for both the gross structure predicted by Bohr and the fine structure observed experimentally. This success significantly bolstered the credibility of the quantum theory and cemented Sommerfeld's reputation as a leading figure in the field. The immediate impact of atomic structure and spectral lines was profound. It provided a coherent framework for understanding atomic spectra, incorporating both quantum principles and classical concepts. Sommerfeld's model became the standard model of the atom for several years, guiding experimental investigations and stimulating further theoretical developments. Physicists such as Wolfgang Pauli, Werner Heisenberg, and Pascual Jordan built upon Sommerfeld's work to develop matrix mechanics, one of the first formulations of quantum mechanics. The work also influenced the development of quantum chemistry. Chemists began to use Sommerfeld's model to understand the electronic structure of molecules and the nature of chemical bonds. The concept of electron orbitals, regions of space where electrons are likely to be found, emerged from Sommerfeld's model of elliptical or subsequent developments in quantum mechanics, particularly the formulation of the Schrödinger equation in 1926. Superseded Sommerfeld's model. The Schrödinger equation, a differential equation that described the evolution of quantum systems, provided a more complete and accurate description of atomic structure and spectra. The Schrödinger equation predicts the same energy levels for the hydrogen atom as Bohr and Sommerfeld, but also accounts for other phenomena, such as the Lamb shift, a small difference in energy between two energy levels. Despite the advent of quantum mechanics, Sommerfeld's work retains significant historical and pedagogical value. It illustrates the gradual evolution of scientific ideas, demonstrating how classical concepts can be adapted and refined to incorporate new quantum principles. Sommerfeld's approach, emphasizing the importance of both theoretical rigor and experimental agreement, remains a valuable lesson for scientists today. His book Atomic Structure and Spectral Lines serve as a comprehensive textbook for a generation of physicists, shaping the way they thought about quantum phenomena. Atomic Structure and Spectral Lines encountered its share of critiques. While Sommerfeld's model successfully explained the fine structure of hydrogen, it failed to account for the anomalous Zeeman effect, the splitting of spectral lines into more than the expected number of components in a magnetic field. This anomaly required the introduction of electron spin, an intrinsic angular momentum of the electron, a concept absent from Sommerfeld's model. Furthermore, Sommerfeld's model still relied on ad hoc quantization rules, lacking the rigorous mathematical foundation of the later quantum mechanics. The reception of Sommerfeld's work was generally positive, particularly among physicists who appreciated its mathematical sophistication and its ability to explain experimental data. Some physicists, however, remained skeptical of the quantum theory, viewing it as a departure from classical physics. Albert Einstein, while acknowledging the success of Bohr and Sommerfeld's models, expressed reservations about their reliance on ad hoc assumptions and their deviation from the principles of general relativity. Atomic Structure and Spectral Lines was directly influenced by Bohr's model of the atom, which provided the starting point for Sommerfeld's investigations. Sommerfeld was also influenced by the work of Hendrik Lorentz and Hermann Minkowski on special relativity, which he incorporated into his atomic model. The Sommerfeld quantization rules were derived from the work of William Wilson and John Ishihara. Sommerfeld's work directly influenced many physicists, including Wolfgang Pauli, Werner Heisenberg, and Pascual Jordan, who developed matrix mechanics. Linus Pauling, a chemist, used Sommerfeld's model to understand the electronic structure of molecules. In conclusion, Arnold Sommerfeld's atomic structure and spectral line stands as a landmark achievement in the development of quantum theory. While superseded by later developments, it provided a crucial bridge between classical physics and the emerging quantum mechanics, incorporating relativity and sophisticated mathematical techniques to refine Bohr's model of the atom. Sommerfeld's work not only explained the fine structure of spectral lines but also shaped the thinking of a generation of physicists. His book Atomic Structure and Spectral Lines remains a testament to the power of theoretical physics and the importance of combining mathematical rigor with experimental observation. Its impact resonates today, informing our understanding of the quantum world and providing a compelling example of the scientific process